In this session, we are going to learn about matrix method for structural analysis. There are two approaches that are commonly used in this method. First one is flexibility or force method, and second one is stiffness or displacement method. In flexibility or force method, all the equations are written in terms of flexibility coefficients or flexibility matrix and unknown forces or moments, and that's why this approach is called flexibility or force method. In stiffness or displacement method, all the equations are written in terms of stiffness coefficients or stiffness matrix and unknown displacements and rotations, and that's why this method is called stiffness or displacement method. And in both flexibility or force method and stiffness or displacement method, we get a set of linear equations in terms of unknown forces and displacements, and we know that a system of linear equations can be conveniently solved using matrix formulation, and therefore these methods are also called matrix methods of structural analysis. Next, we move to solution of truss problem using matrix stiffness method. That is, we will work in terms of stiffness coefficient or stiffness matrix and displacements. Normally in the trusses, we mark the joints by symbols A, B, C, D or some other alphabets. But in the case of matrix method, because we will be writing many equations, we use a slightly different notation which is suitable for computer implementation. So both the nodes, that is joints, and the members or elements are denoted by numbers, and there are different notations in different books. Some books write numbers in circles, numbers in squares, number in brackets, number with underline, etc. Here I am going to use the notation numbers in parentheses for the joints or nodes and numbers with underlines for members. So in this truss, I have three joints or nodes: node number 1, node number 2, node number 3, and there are three members. Member number 1. Member number 1 lies between node number 1 and node number 3. Member number 2 lies between node number 1 and node number 2, and member number 3 lies between node number 2 and node number 3. Here I have also shown one coordinate system, that is capital X and capital Y. Here this coordinate system, capital X, capital Y, I will call global coordinate system, and I'm calling it global coordinate system because this will be applicable for entire structure, all the members. In addition to this global coordinate system, I will also define a coordinate system for each of the member, and I will denote that by small x and small y, and this I will call local or member coordinate system, and this will be local to each member, means each member will have its own small x small y coordinate system. Let's take example of member number 2. Member number 2 lies between node number 1 and node number 2. So for any member, for the two nodes, one number will be smaller than the other number. I will place the origin of my small x small y coordinate system or the local coordinate system at the node with smaller node number, and this I will call near end of the member, and the other end will become far end of the member, and my small x will go from near end to the far end, and y coordinate will be perpendicular to the x coordinate. So this small x, small y coordinate system will be specific for this member number 2, and it will be called local or member coordinate system for member number 2. Similarly, we will define the local coordinate systems for each of the member in our structure or truss. Next, we will discuss the concept of stiffness coefficient. Let's say we are given a member with cross-sectional area A, Young's modulus E, the length of the member is L, and there is a force of magnitude Q acting on the right end of this member, and we know that because of this force there will be a displacement at the right end. Let's call that small d, and we know that I can write the relationship between Q and D in terms of AE and L, and that relationship is Q equals to AE by L into small d. Now if I compare this system with a spring whose stiffness is K, and if I apply a force Q at the right end of the spring, it will displace by amount d. Then I can write the relationship between Q and D in terms of K, and that relationship will be Q equals to KD. Now note that the two equations, that is the relationship between force and displacement for our bar or member and the spring, look identical except the coefficients. In the case of bar, I have AE by L, and in the case of spring, I have K. In fact, these two are equivalent things, and because of that, we call AE by L stiffness coefficient and use same symbol to denote AE by L, that is K. The next concept is stiffness matrix for a member. The stiffness matrix for a member relates forces and moments at the nodes of the member to the displacements and rotations at the nodes of the member. So, for example, take member number 2, which lies between node number 1 and node number 2. The origin of local coordinate system for this member will lie at the node with smaller node number, that is 1 in this case. So the origin will be here. The x axis will lie along the member, and the y axis will lie perpendicular to the member. And note that here we are considering a truss member. Truss members are special members in the sense that they only support axial force. So we can only have either tensile or compressive forces on this member, and correspondingly we can have axial deformations in the member. So in general, there can be 1 degree of freedom at each node, and that will be the displacement along the length of the member, that is d1 and d2, and correspondingly we can have axial forces at the two nodes, and they are denoted by q1 and q2. And here note that I have shown the displacements as well as the forces in positive directions of our local x axis. Now to find relationship between q1 q2 and d1 d2, we consider two cases, and in each of the case I apply 1 of the degree of freedom and find corresponding values of forces at nodes of the member. So in case 1, I apply only D1 and we fix the other end so that there is no displacement. Corresponding to this situation, there will be some force Q1 dash at node 1, and to maintain the equilibrium there will be some force Q2 dash at the other end of this member. And we know from our previous analysis that Q1 dash will be equals to AE by L into D1, where A, E and L have their usual meaning. And if I write sum of all the forces along the member equal to 0, that is the equilibrium of the member, I get Q1 dash plus Q2 dash equals to 0. That gives me Q2 dash equals to minus Q1 dash, or Q2 dash equals to minus AE by L D1. So these two equations denote that if we fix the node 2 of the member and apply a displacement D1 at node 1 along the length of the member, then the force developed at node 1 will be AE by L D1, and force at node 2 will be equals to minus AE by L D1. And here this minus sign denotes that the direction of Q2 should be reverse of what we have shown, and that makes sense because we know that in the case of truss member, the forces acting at the ends of the member are either both pointing towards each other or pointing away from each other, depending on whether we have compression or tension in the member. In case 2, we apply only D2, that is a displacement D2 at node 2 of the member in the direction of member, and we fix the node 1, and corresponding to this, let's say the force at node 2 is Q2 double dash, and to maintain the equilibrium the force developed at node 1 is Q1 double dash. Now from our previous analysis we know that Q2 double dash will be equals to AE by L D2, and from equilibrium of the member, if I write sum of all the forces along the member equals to 0, then I get Q1 double dash plus Q2 double dash equals to 0. This gives me Q1 double dash equals to minus Q2 double dash, or Q1 double dash equals to minus AE by L D2. Here again these two equations denote that if we fix the node 1 of the member and apply displacement D2 at node 2, then the force developed at node 1 will be equals to minus AE by L D2, and the force developed at node 2 will be AE by L D2. In fact, these coefficients can be called the corresponding stiffnesses of the member. Now, because in our original member we have both D1 and D2 acting simultaneously on the member, so the results for original member will be superimposition of case 1 and case 2. So we can write the resultant force Q1 and Q2 as Q1 equals to Q1 dash plus Q1 double dash, and Q2 equals to Q2 dash plus Q2 double dash, or Q1 will be equals to Q1 dash is this AE by L D1 plus Q1 double dash is this minus AE by L D2, or Q2 will be equals to Q2 dash, that is this minus AE by L D1 plus Q2 double dash, that is plus AE by L D2. Here note that we have two linear equations relating the forces and displacements at the nodes of the member, and it is convenient to write this system of equation in matrix form like this, where Q1, Q2 is a vector of nodal forces and D1, D2 is a vector of nodal displacement, and this matrix consists of stiffness coefficients. This matrix K is called stiffness matrix for the member, and note that both these equations were written in local coordinate system. So Q, K and D are the quantities in local coordinate system. Next concept is displacement transformation. Here note that the local coordinate system for all the members will be aligned in different orientation. So when we combine the nodal forces and displacements for different members at nodes, we have to write all the quantities in a consistent coordinate system, and for that purpose we need a coordinate system which we call global coordinate system, which is same for all the members. For that we need to transform the nodal forces and nodal displacements for each member from local coordinate system to global coordinate system, and for that we use transformation matrices. So let's take example of member number 2 again. It lies between node number 1 and node number 2, and the local coordinate system for this is x along the member and y perpendicular to the member, and the global coordinate system has x-axis which is horizontal and y-axis which is vertical. And let's say the angle made by positive direction of small x-axis with capital X-axis is theta x, and the angle made by positive direction of small x-axis with capital Y-axis is theta y. Then we can write the direction cosines of local x-axis as lambda x equals to cos theta x, and if we know the coordinates of node 1 and node 2 of member in global coordinate system is x1, y1 and x2, y2, then cos theta x can be written as x2 minus x1 divided by L, where L is length of the member and can be written as square root x2 minus x1 squared plus y2 minus y1 squared, and whole thing in square root. Similarly, lambda y can be written as cos theta y equals to y2 minus y1 upon L. Using these direction cosines, we can relate the nodal displacements in local coordinate system and nodal displacements in global coordinate system. So let's say at node 1, the displacement in local coordinate system is d1 in small x direction, and at node 2, the nodal displacement is d2 in small x direction. And let's say, and the nodal displacement at node 1 in capital X direction is capital D1x, and that in capital Y direction is capital D1y. And same at node 2 also. Now these angles will be equal to theta x and theta y. Same at node 2. Here note that we know the components of a displacement in two different coordinate systems. So we can write small d1 in terms of capital D1x and capital D1y, and that will be small d1 equals to component of capital D1x along small d1 will be d1x cos theta x, and that I can write as lambda x plus the component of capital D1y along small d1, that will be d1y cos theta y, that I can write as lambda y. And similarly for small d2, d2x lambda x plus d2y lambda y, and these two equations can be written in matrix form as d1 d2 equals to lambda x lambda y 0 0 0 0 lambda x lambda y capital D1x capital D1y capital D2x capital D2y. So if I do the matrix multiplication, D1 becomes equals to lambda x into capital D1x plus lambda y into capital D1y 0 0. Same for D2 also. This system of equation I can write as D equals to T capital D. Here small d is member nodal displacement vector in local coordinate system. Capital D is member nodal displacement vector in global coordinate system, and T is displacement transformation matrix. Similarly, we can relate the nodal forces in local coordinate system with the nodal forces in global coordinate system. So at node 1 we have small q1 along the member, and at node 2 we have small q2 force along the member. And because the truss members can only support axial forces, there will be no other component of force on this member in local coordinate system, and these forces we can resolve in global coordinate directions. Let's call them capital Q1x, capital Q1y, and similarly capital Q2x, capital Q2y, and these angles again same as previous case will be theta x, theta y, and I can write capital Q1x as small q1 cos theta x, that is lambda x, capital Q1y as q1 cos theta y, and that is lambda y. And similarly for node 2, q2x equals to q2 lambda x, q2y equals to small q2 lambda y, and these equations can also be written in matrix form, and that will be q1x, q1y, q2x, q2y equals to lambda x 0, lambda y 0, 0, lambda x 0, lambda y, small q1, small q2. And here note that this matrix here is transpose of this matrix here. So I can write these as capital Q equals to T transpose small q. Here capital Q is member nodal force vector in global coordinate system. Small q is member nodal force vector in local coordinate system, and T transpose is force transformation matrix. So now we can combine the transformation equations with force displacement equation for a member in local coordinate system to get force displacement equation in global coordinate system. So we start with this equation where we have capital Q equals to T transpose small q, and we know that small q is equals to K into D. Here this K is member stiffness matrix in local coordinate system. So this gives me Q equals to T transpose K small d. Now this small d I can replace with T capital D. So that gives me capital Q equals to T transpose capital K T capital D. Here this product can be written as K G D, and here this K G is member stiffness matrix in global coordinate system. Capital Q is member nodal force vector in global coordinate system, and capital D is member nodal displacement vector in global coordinate system. Now we can write this force displacement relationship for each member in global coordinate system, and these equations can be assembled to give force displacement equations for the entire system. Now when we look at our structure, at each node we have 2 degrees of freedom in global coordinate system, that is in global x direction and y direction, and in any structure at any node out of forces and displacement, one quantity will be known and the other quantity will be unknown. Here if I look at my member stiffness matrix in global coordinate system, that is equals to T transpose KT, and if I substitute the expressions or the matrices T and K in our expression for Kg, then I get this expression, and if I multiply all these matrices, I get a 4 by 4 matrix Kg, and the member force displacement equations in the global coordinate system look like this. Here note that each row and each column of the global member stiffness matrix corresponds to a particular degree of freedom. For example, if we look at all the entries in column 1 of this matrix, they all get multiplied with only d1x. If we look at the entries of column 2, they all get multiplied with d1y. So we can say that first column correspond to degree of freedom 1x. The second column will correspond to degree of freedom 1y. The third column will correspond to degree of freedom 2x, and the fourth column will correspond to degree of freedom 2y. Similarly, if we look at the rows of this matrix, all the entries in the row get multiplied with all the entries in this column vector, and this gives us q1x. Because first row gives us q1x, we can say that the first row corresponds to degree of freedom 1x. Similarly, second row gets multiplied with all the entries in this column vector to give us q1y. So we say that the second row corresponds to degree of freedom 1y. Similarly, for third row it is 2x, and for fourth row it is 2y. Now if we look at the individual entries in this matrix, say for example lambda x squared, this corresponds to degree of 1x in the column and 1x in the row. If I look at say this entry, then this corresponds to 1y in column and 2x in the row. So this way we can identify each entry in this matrix with a degree of freedom in column and a degree of freedom in row. Now the stiffness matrices of all the members are assembled to give us the structure or system stiffness matrix that we call Ks. So if we look at the structure stiffness matrix for our truss, which has in total 3 nodes, and each node has 2 degrees of freedom, x and y. So all the columns and all the rows will correspond to those degrees of freedom. So I can write 1x, 1y, 2x, 2y, 3x, 3y for each of the column, and similarly 1x, 1y, 2x, 2y, 3x and 3y for each of the row, and each element in Kg, which is identified by corresponding degrees of freedom in the column and in the row, it will go to corresponding location in Ks is identified by the global degrees of freedom for row and column. And if more than one element are assigned to a particular location in Ks, that is structure stiffness matrix, then they are all added algebraically. This gives us the force displacement relationship for entire structure in global coordinate system, that we can write as Qs equals to Ks ds, where Qs is the vector of nodal forces at all the nodes in our structure, and ds is vector of nodal displacements for all the nodes in our structure. Now in solving these equations, it is often convenient to arrange system of force displacement equations such that equations corresponding to known nodal forces and unknown nodal displacements come on top. Now, if we look at all the degrees of freedom in our structure, they are 1x, 1y, 2x, 2y, 3x, 3y, and some of these degrees of freedom are restrained and some of them are unrestrained. If we look at node 1, 1x and 1y are restrained. So if degree of freedom is restrained, then we know the value of that degree of freedom. In this case, we know that the displacement d1x is 0 and d1y is also 0 because we have a hinge support, but corresponding to these degrees of freedom, q1x and q1y, the forces are unknown. Similarly, at node 2, both degree of freedom 2x and 2y are unrestrained. So the displacements d2x and d2y will be unknown, and the forces at these degrees of freedom will be known. They will either be 0 or some applied forces at that node. So at each degree of freedom, we will know either displacement or force. This can also be achieved if we assign lowest numbers to unrestrained degrees of freedom. So once we organize our forces and displacements in this way, then in our nodal force vector, we will have the known forces in upper part of the vector and unknown forces in the lower part of the vector, and corresponding to these known forces, we will have unknown displacements in top part of nodal displacement vector and known displacements in lower part of the nodal displacement vector, and correspondingly the structure stiffness matrix can be divided into 4 parts: KS11, KS12, KS21 and KS22. And if I do the multiplication in terms of these sub vectors and sub matrices, then I get Q1K equals to KS11 du plus KS12 dk, that is this equation. And similarly Qu I get as KS21 du plus KS22 dk. Now this first equation I can rewrite as KS11 du equals to Qk minus KS12 dk, and if I multiply both sides with KS11 inverse, then I'm left with du equals to KS11 inverse multiplied by Qk minus KS12 dk. So this equation we can use to find unknown nodal displacements, and once we know these unknown nodal displacements, these I can substitute in this equation where only unknown is du, dk is known, and from that we can find the vector of unknown forces at nodes.